Alright, Microsoft Connect, do your job. Off to a good start this morning, it seems, technologically wise. Hey Kevin, how are you? Hooray! And why is this not working now? Ah, good, it's just complete. Aha! Hallelujah, we have success. You would think it'd be easier to deal with this, but nope. Alrighty, so today we're going to basically be combining what we have done for the last couple of days. So we're going to be talking about chemical reactions, and we're going to be using the information we learned about moles in order to talk about how we can do fun math stuff with chemical equations. And this is going to be important for anyone who is interested in making a certain amount of a certain product. This particular reaction that I've written here and already balanced for you guys is a very important one actually, because it produces about, I don't know, like 60% of the world's fertilizer. So you can imagine knowing exactly how much hydrogen and how much nitrogen to combine to make whatever amount of ammonia you want is going to be an important thing to figure out. So, I wanted to display what this reaction means visually for you guys. So, what I've done is I've drawn kind of little ball images to illustrate the molecules that are involved in this. So we have our 3 hydrogen molecules. Those are the blue duets there. And then we have the nitrogen, which is, in this case, purple. And then when we do our reaction, we end up, since this is a chemical change involved, we will be creating 2 molecules of ammonia, and each of them will have 1 nitrogen and 3 hydrogens. And so we're going to be able to get a bunch of information out of here. We're going to be able to see that 3 molecules of hydrogen will give us molecules of ammonia, right? We have to put in 3 molecules of hydrogen, and we will get out 2 molecules of ammonia. We'll do the same thing. We can see that we have 1 molecule of nitrogen will also give us 2 molecules of ammonia. And we can kind of also see that we're going to need 3 molecules of hydrogen to react with 1 molecule of, not ammonia, nitrogen. And so just from this chemical equation, we can see that we can kind of come up with conversion factors that are going to kind of be like a recipe for us. So this recipe is telling us we put 3 parts hydrogen, 1 part nitrogen, and we'll get out, 2 servings of ammonia. And so we can just kind of relate these quantities together by generating those conversion factors below. So notice that these numbers here, let's see, I haven't used green yet. These are our reaction coefficients. And again, you'd get that from balancing, right? So I've already balanced this equation for you guys. And so this kind of recipe that we get is the chemical equation with its coefficients. Mm-hmm. And so we're able to get all of these conversion factors out. And so we're going to be able to today do math with these to try and see, okay, let's say I have a certain amount of hydrogen. How much nitrogen do I need to make all of the ammonia? Or say I want to make a certain amount of ammonia. How much hydrogen and how much nitrogen do I have to put in? And so that's kind of where we're going to be going today. And then after that, we're going to throw in some reality to just mess with you, as always. That reality may be that sometimes we might have something like this, where we have now, for the same reaction, so someone has put in 4 parts of hydrogen and 1 part of nitrogen, but we remember from that chemical equation that we only needed 3 parts hydrogen, right? That's what the coefficient told us. And so if you were to react these, sure, you would get your 2 molecules of ammonia out, but you'd also have some leftover hydrogen. This would be a leftover reactant, you could say. And since it was nitrogen that kind of limited how much ammonia we could make, we had excess hydrogen, right? We had excess hydrogen, more hydrogen than we needed, but we had actually run out of nitrogen before we could keep doing this reaction. And so we're going to be able to call that a limiting reactant. So same thing if you were, making sandwiches. Let's say you were, working at a sandwich shop or something. Does not matter how much, tomato or lettuce or whatever you have if you run out of bread, right? Like, as soon as you run out of bread, you can no longer make sandwiches. It's done. Does not matter how much of the other stuff you still have. It's just not going to be a sandwich anymore without that bread. So in this case, that ammonia, that purple molecule, the nitrogen, that purple molecule, is going to be kind of our bread, and so all that blue stuff would be your tomatoes, and if you want meat on it or whatever, all that stuff will be the blue stuff. And so as soon as you run out of bread, no more sandwiches, you're going to have a bunch of leftover random other bits. So we're going to kind of see that again in the context of chemical reactions here. Okay. So that is our intro for all this. Just because we have, to make things complicated, the chemists have given this the fancy name of stoichiometry. And that is going to be how we're relating quantities of chemical compounds in a reaction. So I'm just going to go ahead and copy one of these conversion factors up here. So we saw that 3 molecules of hydrogen would give us 2 molecules of ammonia. Again, those are the coefficients from the reaction. So this tells us that, say, if we had maybe 30 molecules of hydrogen, oh my gosh, molecules is such a hard word. That would be that would be able to give us 20 molecules of ammonia, right? It's the same ratio. That's the idea here again. So just like yesterday with those limiting reactant things, we are going to see that the ratio is going to be the same. And so if we had, 6 dozen that would mean that we need 4 dozen, or we would get out 4 dozen ammonia molecules, right? It's the same thing. The ratios are the same. Good morning, Tammy. And so, what this all boils down to is that we can then say that we're going to be able to throw in our fun unit of moles. So again, moles are going to be a very, very useful thing for us to work with, again, because it's very hard for us to say, okay, I'm going to pick out 3 hydrogen molecules. We've seen that those are, 10 to the minus 23 grams or something. They're super, super tiny. It's impossible to pick out 3, exactly 3 molecules of hydrogen. And so we're going to see that moles, again, is going to be that useful quantity that we're going to be able to figure out here. And so, if we say, okay, I have 12 moles of hydrogen, let's see how much how many moles of ammonia that would give me. And so, remembering that anytime we see an equality in chemistry, that is a conversion factor. And so we can say, okay, we've got 12 moles of hydrogen. We're going to want to put moles of hydrogen on the bottom, right? And we would just put in those reaction coefficients. And that's going to tell us from this reaction we're going to get out 8 moles of ammonia. Right, nothing too crazy there. Notice, as always, with any unit conversion, moles of hydrogen are canceling out, and we are going to be left with the unit of interest, which was moles of ammonia. Okay, so hopefully that's not too crazy. And so we can also see, if we remember that we had also the conversion factor for nitrogen gas, right? I'm just duplicating it up there so we can see. If we had that 12 moles of hydrogen and we wanted to make that 8 moles of ammonia, we could go ahead and use and see how much nitrogen we would need to put in there. We could do the same thing. You'd say, okay, we have 12 moles of hydrogen. How many moles of nitrogen do I need to react with it? And in this case, remember the coefficient for nitrogen was 1. And so we're going to see we are going to need 4 moles of, what was it? Nitrogen. Oops. So again, moles of hydrogen cancels out. We're left with our unit of interest. Hooray! So this is telling us, essentially, that we need to put together 12 moles of hydrogen and 4 moles of nitrogen if we want to get out 8 moles of ammonia. So it's again just kind of like, duplicating that recipe that we figured out with the chemical equation and now putting it into useful quantities. However, of course, we don't have any instruments that can directly measure moles for us, right? So we do have ones, however, that can measure mass. And so we're going to be able to say, okay, let's say I have 20 grams of hydrogen. How many grams of ammonia will I get out of this? And so just one thing to always keep in mind, anytime you're going from one substance to another, you must use the mole ratio that you get from the chemical equation. So let me just kind of put that in fancy purple. Anytime you go from one substance to another, you must use the reaction coefficients. Oh, that's not going to fit there, is it? Okay. Okay, and remember that those reaction coefficients are a conversion factor. Alrighty, so how the heck are we going to do this? Can we just say, okay, we remember before our conversion factor was 3 to 1 or 3 to 2, right? Can we just say 20 grams hydrogen times 3 moles hydrogen, 2 moles ammonia? No, we can't, right? Because if we look here, the units do not cancel out. We can't just put in grams and throw in our reaction coefficients and hope the answer comes out. Nope, can't do that yet. We will have to do that for sure, but not quite yet. In fact, we have another conversion factor, right, that we talked about yesterday, which was how to go from grams of a substance into moles of a substance. And so what we're going to want to do is use our molar mass So let me go ahead and just, that's the molar mass. 2 times 1.008, right? That's, again, from the periodic table, we found out what hydrogens was. We multiplied it by 2 because there's 2 hydrogens in this case. And that is going to be the molar mass of the hydrogen. Alrighty, and so what we can do here is now that we have moles of hydrogen, we've converted our units. Now we can throw in that conversion factor using the reaction coefficients. All right, and so we're going to see grams of hydrogen cancel, moles of hydrogen cancel. I forgot we're still one more step. Okay. So, since this problem asked for grams of ammonia, right now we are in moles of ammonia, right? So, if we want grams, we know a conversion factor, right? We know that ammonia can be converted into grams. What's its 17.0? Let's see, 2. No, it's 3, something like that. 17.03. I don't know, grams. Something like that. Tyler can double check, I'm sure. Or Kevin, rather. Kevin is our guru of Chem 111. Okay, and so we're going to see that the moles of ammonia should cancel out. Awesome, and Kevin has already done it for us. And so that's going to give us 113 grams of ammonia at the end of the day. So we are able to take our mass of hydrogen, now something we can measure, and using our stoichiometry, that is how we are going to relate these quantities to each other, we're able to see how much ammonia that we can produce in grams against something that we can measure. Just so we're all clear, this was also a molar mass. So we're going to see that whenever we are going from grams of one thing to grams of another, we're going to have these 3 conversion factors. We're going to have the molar mass of one substance. We are going to have the reaction coefficients. That's this part here. Sorry, I didn't do my fancy, ugly bracket. And then we're going to need the molar mass of the other substance. Okay, does that kind of make sense? Oh, we're gonna spend all day doing this. Don't worry. There are a lot of subtle mistakes that students tend to make with this that I want to address right away, and we will do plenty of problems with this. Yeah, so you'll have another 50 minutes or whatever, 40 minutes of stoichiometry fun. Yeah, exciting. Okay. Any questions on this particular one before I do another? While you're doing that, let me just, I know a lot of you kind of like procedures or like instructions. So we're going from mass of substance A to moles of A to moles of B whatever B happens to be, or A, doesn't matter. Anytime you're doing a conversion or a procedure like this, a conversion, remember that here is your molar mass of A, and here is your molar mass of B as the conversion factors, and then here is your reaction coefficients. Reaction is often abbreviated RXN. You'll see that a lot, just reaction. That's what that is. So those are the three conversion factors you would need if you want to do something like this. We're going to learn later on, we don't have to go from mass to mass. There are other things we can do to get moles. We'll talk about gas laws. We'll have pressures of gases and stuff we can use. And when we talk about solutions next chapter, we'll have another one called molarity that will also be useful for us. Okay. Remember one more thing. Molar mass is always whatever grams is 1 mole. Okay, I know that's obvious maybe, but a lot of students, when they see reaction coefficients, they want to put those in their molar mass, which is not something we want to do. So some students will be like, okay, but we have 2, in here we have, 2 is our reaction coefficient. I want to put the 2 there, and I want to make it, instead of 17, I want it to be 34 or something. And that's a waste of your time. Don't do it. Not necessary. We're going to see that molar mass is always over 1 mole. So it's whatever you've calculated from the periodic table over 1 mole. Okay? So don't make that mistake. Alrighty. Cool. So I didn't see any questions there. So here's another reaction for us. It's a decomp reaction, right? We are breaking one substance into another, into more than one. For the interest of time, I'm going to balance this for you guys, if that's okay, or if you want, you can balance it. First one to write something in the chat wins. Do you guys want to balance, or should I? Who's going to be our brave volunteer? No. Kevin doesn't have to balance it. I just want, if you guys want to, if you want me to wait and let you guys practice your balancing, or I can just do it for you. Okay, it looks like half of you have put in. Okay, Noah has finally answered the question. That's good. Okay, but yeah, you guys are right. Balancing this is what you should get. Very nice. Very nice. Very nice. Okay. So, with this, let's say, I don't know, I have 25.8 grams of hydrogen peroxide. So how many grams of grams of water and oxygen will I get once we do this reaction? So 2 problems here essentially, right? I'm asking for grams of water and grams of oxygen. So, we should probably calculate some molar masses first, just to make stuff easier for us. So that's going to be 34.016, 18.016, and 32.0. Okay, I'm just writing the molar masses there. Really? What are you working at, mister? Okay. Now you can be seen for being the evil little thing that you are. Little puffball. Okay. So, there are our molar masses. Again, you would just add up all of the atomic masses of all the elements involved, find that molar mass. So, let's get through it. Or, let's do blue. So it does not matter which one we do first. We can say 25.8 grams of hydrogen peroxide. We're going to first want to get rid of grams of H2O2 by putting in moles. Again, notice that's 1 mole. We do not put the coefficient in our molar mass. Since we're doing water, okay, go away. We're going to want to put peroxide on the bottom, water on the top. And then our last step, we're going to use the molar mass of water, right? Okay, and I'm sure Kevin has already done this math for us. Because I don't want to. Nice. Okay, great. Let me just see if... Yeah, okay, that makes sense. Okay, good. And notice he has applied the 3 sig figs that we started with to the end of the problem. So that's always good, too. All right, and for oxygen, we're going to do essentially the same thing. Starts the same way, right? We're starting with our peroxide. We can then use its molar mass. This time we have a different coefficient because there's only 1 for oxygen. And then we would use the molar mass of oxygen. Okay, and that should be what, 12.1 grams? I can do the math in my head. No, that doesn't seem right. Oh, yes, it does. Okay. I'll wait on Kevin to throw it in the calculator first before I confirm my number. Don't tell me you guys can't do this math in your head. Nice. No, I cheated. I did not do all this multiplication in my head, right? How did I know it would be 12.1 grams? Anybody have any ideas? And again, I'm not some like crazy math savant who can multiply and divide these numbers with all these decimals in my head. Definitely not the case. How did I know it would be 12.1? Any ideas? And no, I did not. I mean, when I teach, I typically just make up the problems as I go. I don't typically do them in advance, so I didn't do that. No ideas? Fine, I'll tell you. Notice that here were our answers, right? Aha, Tyler has it. Yes, exactly. So, remember, conservation of mass tells us that mass of reactants must equal the mass of the products. So, we started with 25.8 grams, and that better be equal to 13.7 plus 12.1 grams. So, if you have a simple reaction like this, where it's, like a decomposition or a synthesis reaction, where there's just a few things going on, you can always use the conservation of mass as well. If you've already calculated one of them, you can just subtract to find the other one. Totally will work. So that's one thing. So, and we're going to see that we're following all the same laws and rules here, right? So we're not violating the law of conservation of mass. We did our calculations, and they have supported that law, right? We saw that we do add these together. It's still 25.8. That's good. We have not suddenly created matter. This is a very good way for you to check your work also, by the way. So if you're wondering, oh, did I plug everything in my calculator right? Just quickly add up your numbers on each side of the reaction, see if they are equivalent to each other. So that is an easy way to spot check. Okay, cool. Any questions on that one? Alrighty. Let's do another one. Okay. So, what's a fun reaction? How about we do... Let's do a synthesis reaction this time. Let's do... I think we balanced this one yesterday, right? We did, or whatever day it was. We did water plus tetraphosphorus dicoxide. It was phosphoric acid. And we had already balanced this, if you remember. I'm actually going to do those in a different color just so it's easier for us to see those reaction coefficients. Let's use green. Okay, let's do this one. And let's say this time I have 100 grams of water and 100 grams of this thing, the P4O10, the tetraphosphorus dicoxide. Looking at this, let's see, will we get 200 grams of phosphoric acid out? I'm going to tell you no, we won't, but let's find out why. So, let's see how much phosphoric acid we can get. Okay, I'm going to go to calculate these molar masses real quick. Phosphoric acid. 97. 97 point, where did it go? 4. Okay, and this is going to be 283.9. And of course, water we had already gotten. We had already had that before. Okay, cool. Alrighty, so there's all the information we have. Let's see how much phosphoric acid we are going to get out of this. So let's go ahead and start with the water and see how much phosphoric acid we get. So just like before, with any sort of stoichiometry problem that we're working with, we're going to make sure that we have our units in moles. Then we're going to go ahead and use our reaction coefficients. times the molar mass of phosphoric acid, which is 97.994 grams per 1 mole of H3PO4. And doing this, Kevin has the answer for us. Or will Star-Lord beat him this time? Let's see. What are we going to have with this one? Hot and shush. Alright, let me see, does that seem reasonable? Yeah, it does, okay. Alright, so before we go any further, let's look at this number. We have 362.6 grams of phosphoric acid. However, we only started with 200 grams on the top, right? We started with 100 grams of each reactant. So that's a problem, right? We can't just all of a sudden come up with an extra 162.6 grams, right? That doesn't make sense. So keep that in mind. Let's just, for fun, go ahead and do the math starting with the P4O10 instead. Let me look up, what is this molar mass? 283.9, okay. Oops. P4O10. E4O10. Reaction coefficients were 1 and 4. And then we'll have that 97.984 again. Just so we are all good chemists. Just like before, our units here canceled out. We're left with grams of phosphoric acid. And here we should make sure our units cancel out again. And poof, there we go. Alright, Kevin, what do we get? Okay, so what the heck? Why did we get such a different number here? And thinking about this one is quite a bit more reasonable of a number, right? Given that we have not created any new matter here, right? We started with 200 grams of our reactants. We end up with, the process for going from grams to grams does not change. So, lucky us, it's somewhat formulaic here. However, starting next chapter, we will be doing other things. So, just keep that in mind. So for right now, the process never changes. So, what these numbers actually mean is, this is how much that could be made from 100 grams of water. And this one is telling us how much could be made from 100 grams of P4 of 10. And so what we're always going to do is we are always going to choose the lower number. we always choose the lower reaction yield. Because if we have 100 grams of each one, we could make a lot more phosphoric acid with that amount of water. However, just like, our sandwich shop, we are going to run out of bread, which is going to be our P4010, quite early, right? We're going to be able to make 138.1 grams of phosphoric acid, but after that, we don't have any more P4010. No, this will work for any reaction, Tyler. But for decomp ones, we don't typically have a limiting reactant because you just have one reactant. So you don't have to do this. Anytime you have more than one reactant, you're going to want to do this. So for combustion reactions or the synthesis ones, or what we're going to find later, the single or double replacement reactions, will also need to do this. Okay, so this tells us that we can only make 138.1 grams. And we have a fancy name for this. This is called the theoretical yield. That's how much we could make before one of our reactant runs out. Let's see, can I make this work with... but I was going to maybe do an example where I'm pairing the dogs off or something with brown dogs and white dogs, but forget it, it's going to take too much time. So our theoretical yield is how much we can make of whatever product we're looking at before one of the reactants runs out. So after we've made 138.1 grams of phosphoric acid, we have run out of P4010. We can no longer make any more. Okay, so even though we could have made more if water were our limiting factor, water is not. So in this case, P4010 is a limiting reactant. So that's the one that ran out. And therefore, water is the excess reactant. And so, if we, there are a number of ways we could find out how much water is left over. Presumably, we will use all our P4010. There will be none of that left. We will have made our 138.1 grams of phosphoric acid. And if we wanted to find out how much water is left over, we remember we put in uh, 100 grams of P4010. Remember, we got out 138.1 grams of phosphoric acid. And so we remember we have, again, our law of conservation of mass, telling us we put in 200 grams. Where the heck is the other 60, whatever, 61.9 grams? That's actually going to be leftover water. No, that's not. 61.9, I said, I think. Right, so we, in fact, have this extra water, extra of our excess reactant. Right, so that doesn't gone anywhere, it's just sitting there, it's extra. So like before, if I may scroll up way back when we had the leftover reactant, it's just kind of sitting there unreacted. Right, so when you have an excess, we're going to be able to calculate it through a number of ways. All right, easiest way is use our conservation of mass, right? If we just have two reactants and one product, we can very easily see how much our extra is going to be just by using conservation of mass. All right, there are other ways though. If we really wanted to be very good chemists, and I'll show you this, but right now you can totally use conservation of mass, but I'll show you how we can calculate the excess. And what we're going to do is we are going to convert theoretical yield into excess reactant. For this problem, that means we are going to be converting our H3PO4 into water. We're going to take our 138.1 grams of phosphoric acid and convert that into grams of water. And so, by doing that, just like before, anytime you're converting from one mass of one substance to another one, we do exactly the same thing. We're going to, what was the 97 point, unequal, okay. My goodness. We're just going to be doing the same thing that we've done before, but now it's in reverse. Oh goodness, I don't remember our reaction coefficients. We had 4 for phosphoric acid, 6 for water. And then doing this, we're going to multiply that by the 18.016. And from this, we are going to get, I'm just doing the math in my head real quick. I'm cheating again. Oh, duh. Okay, and this is the amount of water we actually used. So in order to make that 138 grams, we used 38.1 grams. Starlord, it will totally work for simple reactions. Totally. A lot less work, I agree. If you can use it, go right ahead. But we're going to see that if we have more complicated reactions with like more than 3 things, sometimes it might not work as easily. So just keep that in mind. So for like simple stuff like this, yeah, totally. Save your, your brains. Very easy that way. And so the amount we have left, if we were to do this, the amount left over is the starting amount minus the amount used, which is going to be, we started with 100 grams and we used 38.1 grams, and so that's going to be the 61.9 grams water left over. So if we have a more complicated reaction, this is how you could solve for the excess reactant. But as we have pointed out already, for right now, if you have a simple reaction like this, save your breath. Go ahead and do your conservation of mass. That'll save you a lot of time and energy and brain power. Okay, but this should all be pretty logical also. Even though right now we may not need to use this to find our excess, does this kind of make sense as to why this works? So we're using our theoretical yield, the amount we could have possibly made with all of those reactants, and seeing how much we would actually use of our excess. And then from there, we're going to be taking what we started with, subtracting what we used, and seeing what's left over. So just like before with that hydrogen thing, we started with 4 hydrogen atoms. We used 3 of them. We had 1 hydrogen molecule left, right? And that was those lovely pictures that I drew. Okay, but yeah, totally for sure right now, boom, we have our conservation of mass. Save yourself some time. Okay? Julio. All right, any questions on this problem? So anytime you are given masses of 2 different reactants, you're going to have to do the process where you do both calculations. And you'll always choose the lower number. Okay, so let's do another one of these. Oh my goodness. Okay. What reaction should we like to do? How about... Yeah, okay. By the way, this stuff is in your homework. The packet of questions that I posted, there is a section on this stuff. So you will see it. Let's take, I don't know... Okay, let's use these 2. Combustion, what about combustion? You want to do a combustion reaction? Oh, sorry, Kevin. No, I totally know, yeah, I was, that was more of a question just asking to myself. So combustion, oh gosh, calm down, creature, I stepped on him, whoops. Okay, let's do with this one. So let's say we have this much. Okay, what is the theoretical yield of sodium chloride? So we have the mass of 2 reactants here. We can go ahead and do the same thing where we do both of them, just like before. 58.44. Okay. Isn't this so like embarrassing? I have all these like memorized. Ugh, how awful. Okay, cool. 5 grams sodium times, oops, Does anybody have any questions with like how to set this stuff up? I mean, I understand we're doing the same process over and over and over again, so it's probably becoming pretty like boring. But if you have any questions, throw them up. That's why I'm here. 58.44 grams, 1 mole. And while Kevin is calculating that, I'll just throw out the process for the second part reactant. Again, nothing new here. And I understand I'm going pretty fast, but again, this is exactly the same as we've done before, so nothing brand new with this problem, just another example. Okay, and so while Kevin is calculating those, we have one more part. Okay, awesome. I assume that was for the sodium, right? So while he's calculating the next one, let's look at that number. 12.7 is already higher than the mass of our two reactants, right? If we add up our two reactants, we're going to see that's 12.5. Star-Lord, that's the reaction coefficients. That's these two numbers. So it's not saying there are 2 moles of sodium in moles of sodium chloride. However, we can see there would be 2 moles of sodium in 2 moles of sodium chloride, right? 2 in each one. It's the same thing as 1/1. But it's always good practice to write out your full coefficients even if they are equivalent to each other. So hopefully that makes sense, Starlord. They're just the reaction coefficients. Cool. Okay, so I'm just going to delete those circles. Okay, cool. And then, boom. So already we can see, this first one didn't make sense. 12.7 would be more than our reactants would add up to, so that can't be the right answer. So let's just make sure our other one can. That's the smaller one. Remember, we always choose the smaller number to be our theoretical yield. And does this one make sense? Yeah, it totally does. We can see, okay, we had 12.5 grams put together. We ended up making 12.3 grams. If we use our conservation of mass, we'll have 0.2 grams of something else left over. In that case, it's going to be sodium, right? So chlorine is limiting. And we could make 12.3 grams of our sodium chloride. Alrighty. So, questions on that one? Again, same idea. When you have the masses of 2 reactants, you're going to want to calculate for both of them and see what you get. It's the one that led us to the smaller number. So we started with chlorine, and we got the theoretical yield out of that one. The sodium that we would have started with ended up giving us excess. And so sodium is not going to be our limiting then. The reactant that gives you your theoretical yield, whatever you start with to get that theoretical yield, that's the one that's going to be limiting. Does that make sense, Karen? Awesome. Okay. All right, last wrench for you guys is, you probably noticed we have this word theoretical here, yeah? And as we often know, reality does not like to agree with theory. For whatever reason, let's see. Correct, exactly. So chlorine will run out, and so we will have extra sodium hanging around. Exactly. What was I saying? Oh yeah, reality. So in reality, it's nice to say, okay, the sodium and the chlorine are going to react together, they're going to be perfect, and we're going to make our 12.3 grams of sodium chloride. However, perhaps some of the sodium reacts with oxygen instead, or the chlorine escapes out of the beaker that you're doing, or whatever. Reality happens, and we have one more term that we're going to be able to use to describe this. So let's say in theory we could have made 12.3 grams, but let's say in actuality this number I'm giving you, by the way, you would not be able to very easily just, you can't, I'm just making up this number. only to describe our last term here. We have a term called the percent yield of a reaction. And that's going to be the actual yield over the theoretical yield times 100%. And so in this case, the reaction yield, if we only made 10 grams, would be, in this case, I'll do the math, 10 divided by 3. So this reaction was 81.3%, like, efficient or whatever. So that is the percent yield for this reaction. So again, I've just kind of thrown out that number 10. Both, okay, so Taylor, cadmium is a fixed charge transition metal. Aluminum has a fixed charge, but it is not a transition metal. If I'll just take a moment to do that, boom, periodic table. Right. Okay, we have aluminum right here. We have zinc, cadmium, silver, right? I told you guys to remember 3, 2, 1. Transition metals are only this stuff. Aluminum is in group 13, so it's not a transition metal. Okay, but both cadmium and aluminum have fixed charges. Okay, so basically this last one should not be too crazy. Easy formula for you guys. I could tell you, okay, the reaction only produced this much. What's the percent yield on the reaction? And you'd be able to calculate it. Or I could give you a percent yield. Let's do that actually. Okay, so I know we're running a little bit over time, but that's nice. I don't care. I'm here for you guys, right? Okay, so let's say our theoretical yield before for this phosphoric acid was 138.1, right? Sorry to just jump all over the place like this, but I wanted to get you guys out of here so you can, I don't know, do whatever you do. So this was a theoretical yield that we had calculated previously. What if I tell you this reaction the yield was 67.3%, we could calculate the actual yield. By understanding that, again, it's just a formula, right? We have percent yield is actual over theoretical times 100. So 67.3 is x over 138.1 grams times 100. X equals, let's find out. So just showing you how you can use theoretical yield in a different way. 138.1 times 0.673. So again, just like any other formula, I would give you two of the variables, right? And you would solve for the third one. Okay? So that's, yeah, perfect. Ah, sig figs, Shane. Got you. Oh, well, actually, you might, well, depends. Presumably this theoretical, or this reaction yield should give us, yes, it will be, Karen. This is still part of chapter 3, so it will definitely be included there. So, I understand today's Thursday. But as you guys probably already know, I am almost always on Discord available to answer your questions. So, you know, I'm always happy to say, say, hey, I'm really stuck on this homework problem or whatever. And yeah, it should be a measured number, so it should count for sig figs chain. It's actually a calculated number, but let's count it for sig figs. Okay, cool. So, with that, the poll will close tomorrow on, like, again, it looks like multiple choice is completely overwhelmed for your response, so chances are you will have a multiple choice exam. I will again try and scrounge around, see if I can find a practice one for you guys. We'll see. I will send out an email this weekend about how the exam is going to work. Like kind of the sorry, Shane, I shouldn't have thrown that wrench at you. I'll send an email this weekend how the exam is going to work. Again, I'm going to post your homework answer key on Monday at 12:01 a.m. So you'll have all of Monday to take the exam. So, if you want to wake up at 9 in the morning and then, take a look at the homework key and do all your stuff, that's fine. And then just take the exam later in the day. That's totally okay. So, look forward to that email. I guess I have to... So far, it's going to be everything, yeah. Everything we've done so far. So, just preferentially, the stuff we did on like the first couple days is kind of like boring. I will probably not focus on that as much. So yeah, definitely like naming reactions. This mole stuff would be probably the most important stuff we've done so far. And of course, sig figs. Never forget sig figs. So you're lucky, by the way, if it's multiple choice, like I can't really get you on the sig figs there as easily, except in questions that specifically ask for sig figs. So, yeah, it's good stuff. Okay, anyways, any last questions? As always, head to Discord, post your questions there, help each other out. I'll be, of course, poking into to help out as well. So, yeah, that should be good for you guys. Okay, cool. So, with that, enjoy your weekends as much as you can. Again, I'm not going to stream on Monday because that's your exam day. So I will see you on Tuesday instead. Alrighty, and that we're going to start dealing with electron structure, which is even more fun. So, fun. Okay, sounds good. See you guys. Take care. Turn that off.